So, hello everyone. Here we are with Kresimir Josic from the University of Houston for our October Matbio seminar at UTEM. Um, so the seminar will be in English. And let me briefly introduce our speaker. He has a bachelor in mathematics and physics, then a PhD in mathematics at the Pennsylvania State University. Um, he's a professor at the Department of Mathematics at the University of Houston with adjunct appointments in biology and biochemistry at UH and biosciences at Rice. Member of the mathematical biology group of the university, I guess, and lead the Gulf Coast Consortium for Theoretical and Computational Neuroscience. So a very experienced mathematical biologist that I happened to meet at the conference in Philippines early this year. So very glad to have you here, Kresimir, and please tell us about your work on uh, fast decision reflect biases, slow decisions do not. Thank you.
All right. Thank you. So thank you again for the invitation and thanks for the opportunity to present. I'm going to give a little bit of an overview of this work. And so this is work I usually forget to acknowledge people. I often forget to acknowledge people that I work with. So just to, in the beginning. By the way, can you see my cursor?
Yes,
Do you see my
yes, we
cursor?
see.
Yeah,
Yeah.
okay, good. All right, good. Yeah, so it makes it easier to point. This is a few people from University of Houston, including Megan and Simon, who were my postdocs. Oh, sorry, graduate students, and Willot, who is a faculty member, Zach Patrick, and Benji Lindner are professors at these universities. Barga was a postdoc. He's a Florida State professor at Florida State right now. Sean is I'll tell you a little bit of a story about how Sean was involved in this. He and is a professor at the University of Utah, and Samantha as a graduate student currently at the University of Utah. Okay, so just a brief outline. So there's essentially three papers that I'm going to talk about. So the question is, how is evidence accumulated? And I'll tell you a little bit about what I mean, not a little bit, I'll tell you what I mean exactly with the evidence accumulation decision social networks, right? And so I'm going to start with what evidence accumulation means in the case of a single decider, and I'm going to talk about decisions of social networks. And then we're going to talk about there's these three topics that I'm going to essentially that are essentially three papers. One is about how heterogeneity improves speed and accuracy. Another one about correlated information, and the last one is going to be the title of what we just talked about. The fastest decisions reflect initial biases, slowest decisions do not. Right. This was the title of the talk. Right. But I'll tell you a little bit more. Okay, so where this started was essentially when I was, I think by now it's 7 years ago that I reviewed this paper, so I can say that I reviewed it. I mean, it was published and it's, it was being cited in the literature. And so this is a paper by my good friend Brent Doran and actually a high school student at the time, Reggie Kaginalp. So Reggie is quite talented. He's a graduate student now at Berkeley. So the idea was, what they did was to try to understand how decisions are made in groups on social networks, really, when people interact. And when I read the paper, I thought that they didn't quite do it right. So, I started thinking about how to do it from a Bayesian perspective, so in a corrective Bayesian way. And that was kind of the motivation for all of this, right? And so it really comes back to, that's why it's useful to sometimes review papers. You get some ideas about how to extend things, and at least you're forced to read them carefully, right? And then that often gives at least me ideas about how to extend things. And so let me tell you what I mean by evidence accumulation. This is kind of the evidence accumulation that people often talk about in neuroscience and in cognitive science. And the idea can be illustrated. This is not the types of problem that's necessarily, but it's an abstract illustration of a general phenomenon, of a general model that appears, and it's used often in a very simple setting. So the idea is that it goes back to Wold and Wolfowitz, Turing and Neyman and so on. And so people since the 30s have been really working on this idea. Really, the big name is Wold, Wold and Wolfowitz are the two who probably who were the ones who established the theoretical background for this idea. And so the question is, you have two different coins, right? They look identical, but one comes up predominantly heads, one comes up predominantly tails. And I give you one of the two, right? And you can flip it a few times, you can toss it and see the outcomes. And the question is, how do you decide whether I've given you coin one, which comes up heads most of the time, or coin two, which comes up tails most of the time, right? You can only toss them. It's the only way you can tell which one I've actually handed to you. And the idea, that Wold and Wolf, it's actually not that hard to come up with, right? The idea is to really use Bayes' theorem and say, okay, I have two hypotheses. Hypothesis one is that I've given the coin on the left. Hypothesis two, H minus is I've been given the coin on the right. What I do is I toss it several times. So I make observations. Those are the psi 1 through t. Those are observations of heads and tails. And I know the probability p, right? If you know the probability p, you can use Bayes' theorem to write the log likelihood ratio yt of the probability that hypothesis plus is correct given the sequence of observation versus the probability that hypothesis minus is correct given the sequence of observation 1 through t. You can write that recursively as the log likelihood ratio after the previous flip, this is yt minus 1, plus the log likelihood ratio of the two observations that you see heads or tails under hypothesis plus or hypothesis minus, given the current, after the observation that you just made of the flip, right? So this now gives you a nice recursive equation. This is this term right here is the log likelihood ratio that you obtain after the flip at time t, after the tth flip. And this is the log likelihood ratio yt minus 1 was the likelihood ratio of the previous flip. And so you can just recursively update the log likelihood ratio. What you get is that your belief or the log likelihood ratio goes up every time you see heads and goes down every time you see tails. The optimal way to then stop is to set a threshold a priori of theta. And when your log likelihood ratio exceeds that threshold, make a decision. If it exceeds the positive threshold, theta, then you decide plus. If it exceeds the negative threshold, you decide minus. The higher the threshold, the more evidence you need, and the better the decision, the more likely that you're correct. The lower the threshold, the faster the decision. The lower the threshold, the faster the decision, but also the more likely it is to be incorrect. And so this is the optimal, setting a threshold in this way is the optimal way to make these decisions. It's the optimal trade-off between the speed and the accuracy of your decision. And this is again shown by Wald. And this is a model that's been used over and over again well, it's the optimal model, but it's also, if you assume that P goes to 1/2, P here goes to 1/2, so that your information that you get from every single toss of the coin becomes less and less informative. And in the limit, as you take more and more flips, this model, the discrete model on the left, actually approaches a drift-diffusion model. It has a constant drift and a diffusion term over here. I'm going to assume that this 2m can be generalized to not just these m and the diffusion constant can be more general than this. But this is what's called a drift and diffusion model. It's a really simple ODE model SDE model that's been used over and over in the literature. There's probably thousands of papers that use this particular model, the one on the right, to model, for instance, decisions of pedestrian crossings, attentional drift diffusion, sub-purchasing decision, and so on. And so on and so on. And so it's probably the model that explains very, very clearly also how in this case, animals is a very standard experiment where you have a macaque, watching dots that move randomly across the screen, and some percentage of the dots move coherently to the left and to the right, and the monkey needs to decide which direction the coherently moving dots actually move. And when this percentage is very low, up to 2 or 3%, it looks like there's actually nothing happening. It just looks like a random motion of dots. The monkeys get really good at this, and their decision behavior, their decision making, is very well described by this drift diffusion model. So a model where there's an internal variable that keeps on randomly moving and until it hits a threshold where a decision is made. Okay, and so this is again, this is work by Newsom, Shedlin, Josh Gold, and many others who have used this drift diffusion model in cognitive science and psychology and in neuroscience to describe decision making in mammals and other animals as well. Again, so this is the model that I will use. I will take this. I will take the view that this is a optimal model. That I think take the Bayesian view that this is an optimal model, and see what the implications are. Okay, so the question then is: this is again the decision making for a single individual, right? So how do we extend that to a group of people? So in particular, if you want to decide whether to buy it, in, so now at least in the U.S., but I think probably everywhere, people are trying to decide whether to buy a new iPhone or not. So you can read, you can make private observations or read reviews, gather evidence on your own, but you can also get information from your friends and colleagues, right? So this is social information that you gather. And so this is the idea that we're going to look at. So you're going to here's an animal trying to escape from a predator. It will also gather its own private information about to decide whether to move to the left and to the right, right? So essentially what the terrain is like, where the predator is, and so on. But it will also look at its conspecifics, right? So it will also look at other antelope, where the other antelopes are moving to get some social information about what is the best decision. And this idea of making group decision really goes back, over 300 years, if you think about, or 200 years. If you think about Condorcet's jury theorem is an example of this type of decision of the trying to have a mathematical model of what this decision-making process looks like. I just quoted a few of the most famous papers in this area. Most of the time in these papers, except for really the last one, the way evidence is not accumulated, however, right? It's the social evidence sometimes it's accumulated, but the individual evidence is not accumulated. So the idea is if the entire group tosses a coin just once, there's one observation, and that information is exchanged, right? So there's no continuous accumulation of evidence. And so that's the model we'd like to look at, right? So where we have this drift diffusion process, which models an accumulation of evidence, which terminates in a decision. And the question is, what if the evidence is accumulated and exchanged? How does a group make decisions, right? And so the first paper I'm going to discuss briefly is this evidence accumulation on social networks. This is again work with these 5 people. And the question is, so first of all, let me just give you a background on how we extend the evidence accumulation model. The simplest way to explain this is in a case where you have one individual, one agent, making a sequence of decisions. Again, you can think of this as a sequence of coin tosses, coin flips, and a second agent who also makes a sequence of private coin flips, right? So this is private information. They do not share that information. However, in this simplest of models, agent 2 can observe the decisions of agent 1. Right. So in other words, agent 1 needs to decide between 2 hypotheses, H plus and H minus. Agent 2 does not see the private evidence that agent 1 accumulates, but sees the sequence of decision that agent 1 makes, including a non-decision. Right. So think of them as they both get a coin. It's the same type of coin. It's not the same coin. They don't see the same coin. They get the same type of coin. They flip the coin, right, independently. And then one of them, agent 1 reaches a decision and communicates the decision to agent 2, but not the other way around. That keeps it simpler, and I'll tell you why in a moment, why that's simpler than kind of looking at connections going both ways. The decision state is 1 if agent J chooses H plus, 0 if agent agent 1 in this case does not make a decision at time t after the teeth flip, and -1 if they choose the opposite, right? So there's 2 choices. I'm going to always talk about 2 choices. This can be extended to multiple choices, but it gets more complicated. Okay, so again, all agents want to determine whether the state H plus or H1 minus is more likely. They can receive probabilistic evidence. They can never really be sure about which decision is appropriate, which coin I handed them. But they, by accumulating more evidence, they can be more sure about the outcome. They assume that they accumulate evidence that the log likelihood ratio, the variable yt that we discussed before, moves stochastically and make a decision when it reaches a threshold. They make independent sequential observations, so they're independent in time and between the two of them, right? So these are the coin tosses are independent. They make a sequence of observations of stage from measurements from some measurement distribution that they know. In other words, they know the probability p that the coin is going to come up heads, but they don't know which coin they have, right? If this is not the case, if they don't know the measurement distribution, things become more complicated. You have to marginalize, but the ideas are not that much more difficult. They do not share their observations that we said, but they share their decisions. They share the decisions, so they can observe it. If they share the observations, then effectively what you get is as if agent 2 observed just twice as many tosses as agent, as it does on its private. So that's kind of an uninteresting problem. It just reduces to the previous problem. And we'll assume that the thresholds and these measurement distributions are known for all the agents. That just makes it a little simpler. Okay, so the feed-forward network. So again, agent 2 sees agent 1. Agent 1 does not see agent 2, right? So decisions of agent 2. Agent 1 makes a number of private observations, right? So this is their log likelihood ratio. Their belief is exactly the same as if the agent 1 was the only agent in the world. There's nothing really complicated happening here. But agent 2, actually, the way that the log likelihood ratio of agent 2 changes is as if it has it's essentially can be decomposed as a sum of the private information, which is exactly the same as the one for agent 1, and then the social information. And the social information is the log likelihood ratio of a particular sequence of decisions from agent 2. If theta plus and theta, if the two thresholds are exactly symmetric, then a non-decision is uninformative. So not seeing a decision, right? The absence of a decision is uninformative if the two thresholds are symmetric. If they're not symmetric around 0, then a lack of a decision can also be informative, right? So that's a special case. I'm just going to talk about symmetric decisions just to keep things simple. And then if agent 2 sees a decision from agent 1, it would update their belief. Their log likelihood ratio, yt, is going to be updated by exactly the amount of the threshold of agent 1, right? So the threshold theta is the amount of evidence that agent 1 needs to make a decision. If agent 2 sees a decision, it will update its belief by exactly that threshold. I mean, if you think about it, that's not really that difficult to believe, right? So it takes a little bit to prove. It really just comes to formulating the assumptions correctly, and that threshold then is added to the belief of agent 2. If you have recurrent networks, things get a lot more complicated. There is essentially, you get into these recursive behavior. So if agent 1 and agent 2 can see each other, non-decision in particular are informative, or you can kind of continue with the ability to change a decision. You get into these really complicated issues where agent 1 has to know what agent 2 knows, and take into account what agent 2 knows, and that agent 1 knows that agent 2 knows, and gets recursive and back and forth and so on. So I'm going to avoid this. This is kind of related. I don't know, in the US, I always put this slide. I don't know how many people know this movie. This is The Princess Bride, and there's a scene where this Vizzini always tries to figure out whether there's poison in his cup. If you haven't seen it, you can look it up on YouTube. It's a little funny clip that kind of, I think, illustrates this idea of common knowledge that goes back to Aumann and others in a pretty kind of a funny way. All right, so what we're going to talk about is decision-making. So now that we have this, the main idea is that once a decision is reached, everybody updates their likelihood, of their log likelihood, their belief, by an amount theta, where theta corresponds to the threshold of the decision that's reached. So what we're going to have now is a network, is a clique. A clique just means everybody sees everybody else of agents. they have possibly different symmetric thresholds. So the threshold plus and the threshold minus is symmetric around zero. And an absence of decision is therefore uninformative. So if you don't make a decision, it doesn't change the other people's beliefs. Every agent is rational, so the Bayesian agents, so they make the best possible use of the available information. And we're going to look at a continuum limit where they accumulate information in the way that we've just talked about. I'm assuming the M here is 1, just to you can non-dimensionalize time to get that. Okay, so here's the idea. So in this case, one agent is going to make a decision that's going to cause everybody else to update their belief by theta. For some of them, so some of the agents, in particular agents whose belief, if all the thresholds are the same, then then the ones whose belief is between 0 and theta, they're going to follow the decision of agent 1. The remaining agents, the blue ones who would not make a decision, meaning their belief is between minus theta and 0, are going to now be able to observe how many agents followed the decision of agent 1. And that means that the other agents actually revealed to the blue agents, the ones that follow agent 1's, revealed to the undecided agents that their belief is between 0 and theta. All the other undecided agents reveal to each other that their belief is between minus theta and 0, right? And so now the undecided agents can take that into account and update their belief again and make a decision, right? And so the question is, do all agents decide, and how good is the collective decision? All right, so I'm just going to give you an outline. I'm not going to go into the mathematics too much. The way you do this, the way you do the asymptotics, is to solve essentially the Fokker-Planck equation, approximately solve the Fokker-Planck equation on the domain negative theta to theta, and using a method of images, you can find that the expansion at small times is given by this expression, and you can use asymptotics to essentially use these Gaussians, use essentially Gaussian integrals and so on and the asymptotics of Gaussian integrals to get to the results that I'm going to tell you about in a moment. All right. So here's exactly what I said. So one agent makes a decision. All agents update their belief by theta. So their belief jumps by theta or minus theta. I'm assuming the first decision is positive. So the first decision is, so everybody updates their belief by theta. Now, A1 is the number of agents that agree now with agent 1, whose update now causes them to update the belief above their own threshold. And so this is the first wave of agents to make a decision after the first decision. And these are the agreeing agents. And so these are agreeing agents. The remaining agents, right? There's n minus a1, so this is the ones that agreed, and minus the 1, this is the one that made the first decision. These are remaining undecided agents. And as I said before, the belief is between minus theta and 0, right? Because if it's between minus theta and 0, you add theta, that means that it didn't cross threshold, right? So they are still undecided. The remaining agents now know that every agent who agreed now gives the remaining undecided agents this much information. They can update their belief by this much, R plus. This is the log likelihood ratio that their belief is between 0 and theta under hypothesis plus, and divided by the probability that their belief is between 0 and theta, given that the hypothesis is minus. And again, I told you that you can get these probability distributions, you can approximate these integrals using the method of images, and these integrals essentially involve some Gaussian integrals which you can approximate, right? And then you take the log of these and use some expansions and so on, which I'm not going to go through. It's a few pages of calculations, but it's not hard calculations. It's straightforward calculations. Again, every disagreeing agent now takes the log likelihood ratio of the opposite. We know that their belief, if they're disagreeing, their belief is between negative theta and 0, and we take the probability that their belief is between negative theta and 0, given under a hypothesis plus and under hypothesis minus, you take the log likelihood ratio of that. That gives you the evidence if you observe in undecided agents, and this is the evidence from the deciding agents. So everybody who is undecided now updates their belief by A1. This is the number of deciding agents. Each one of them provides this much evidence, R1 plus, R plus. This is the number of undecided agents, n minus a1 minus 1, and then you also exclude yourself. So you have n minus a1 minus 1 agents, but you also exclude yourself because you're not going to count your own evidence. So every undecided agent counts the number of remaining undecided agents, and each one of those gives them an update R minus, right? And this is the belief increment in the second wave. Now, in the second, this is going to cause some of the other agents to update their beliefs and make decisions, and then that's going to then reveal further information, which you can also go through further rounds. And the question is, when is this going to stop? Is it going to stop if the population is large, right? If you're taking a asymptotic limit of a large population, so you can use some of asymptotics for these integrals, right? And if the population is large, you can actually show that the number of agents that agree with the first decision is about half of the population. And if the first decision is correct, then you get an additional term plus theta n divided by the square root of 8 pi log n, right? So this is it's a little bit, it's a bit above the half the population that makes that agrees with the agent. And if the first decision is incorrect, then you use the same expression but with a minus sign. So it's a little less than half the population. And the update that they make is essentially goes like theta over the square root of log n. This is the update, the amount by which the expected amount by which the population updates their belief, right, for each agent that decides. Again, this is a random quantity because the time of the first decision, the t here, is random. The time at which the first decision is made is random, and it becomes smaller and smaller the more agents you have, right? The more agents you have, the quicker the first decision is. The quicker the first decision is, actually, the smaller the amount of information that everybody provides because their beliefs, they haven't had time to accumulate a lot of information. And you put this together with this expression that I gave you on the last slide. These are all the things that you need to put together, and you get an expression, dropping some terms that are not important. You get essentially that the update is n over log n, goes like n over log n, right, with the population size, meaning the update becomes larger and larger as the population size becomes larger, which tells you that the dynamics is actually like this. We'd probably skip this. The dynamics is like this. So one makes a first decision, about half the population follows either a little bit more if the decision is right, a little bit less if the decision is wrong, and then the second wave follows. And if the population is large, the second wave is going to be the entire population, right? It's going to be the entire population. If the first decision was correct, the entire population follows the first decision with high probability. If the first decision was wrong, then about half the population is going to make the opposite decision, meaning it's going to be self-correcting, right? So this is the important thing. You go through this. This is always going to be positive. Sorry for skipping around. This is always going to be positive. This is always going to be positive whether the first decision is right or wrong, meaning it's always going to be correct. This update is always going to point in the correct direction. All right, and so just to maybe I'll skip this. This is just to say that the asymptotics work, right? If you the ones that I've talked to you about, and this is the probability whole clique makes a decision if the population is sufficiently large. Sorry, the whole clique does decide by the second wave, essentially, right? This is numerically. You can get a lower bound on this using Chebyshev's inequality. So just to recap, in large networks, everyone decides by the second wave. Everyone follows the correct first decision. If the first decision is incorrect, then you have about half the population that follows an incorrect first decision, also makes an incorrect decision, but then a second, slightly larger population is self-correcting, right? They will make the correct decision. Right, incorrect first decision, half people follow, make an incorrect decision, and then the other half, a little more than half, correct themselves and make a correct first decision. Make a correct decision. All right. So how is this used? So how can we use this? So I'm going to talk about now population where about some fraction gamma, which could be small, has a low threshold. So this is going to be the heterogeneous population. Some fraction gamma is going to have a low threshold, and a fraction 1 minus gamma is going to have a large threshold, right? And so This can be done with a distribution of thresholds, a decision threshold. So essentially what you have is a population, a small fraction of the population, doesn't have to be small, but some fraction of the population that decides, makes quick decisions, right? They need little evidence to make a decision, and another fraction of the population that needs a lot of evidence to make a decision, right? And so what we're going to look at is how to make use of that, right? And so let me just tell you the story here. I'm not going to go through the asymptotics. If you make the population, this fraction that with a low threshold, if you make it very small, the rest of the population, remember this is a clique, everybody gets to observe everybody else. The rest of the population looks at the small population. Remember, this population is essentially, they make very quick decisions. By the time this small population makes a decision, the rest essentially don't have an opportunity to make a decision, right? So really, this population these are the early adopters. These are the ones to make they need very little evidence to decide one way or another. Really, what happens here is that if there's too few of them, they're not going to influence. Their theta is small, and they're not going to be able to influence what the larger population does. They're going to make bad decisions because they have a very small threshold, but the rest of the population is going to be uninfluenced because this is a small fraction, essentially. They're not going to be able to sway. If this population is very large, if this population of early adopters, of people with low thresholds is large, then the opposite is going to happen. Most of the population is going to have a small threshold, and most of the population is going to be wrong if the first decider decides wrong. Right? If the population is just right, somewhere in between these two extremes, then you have these early adopters, right? That make about half of these early adopters, if the first decision is wrong, about half of these early adopters are going to be wrong. But the rest of the population gets to see who agreed with the first decision and who disagreed with the first decision. And they are all, as a result, they're all able to make a correct first decision. Right, and so you can sacrifice a group of early adopters, so that the rest of the population, which need more evidence to make a decision, all make the correct decision. Right, and so in the heterogeneous case, a relatively small group. This is about log n of the entire size of the population, or I think it's actually, now that I think about it, I think it's the square root of log n of the entire population. Can be sacrificed, so they can make they can make a bad decision. Half of the time they're going to make the wrong decision, but the rest of the population is going to be able to use that to actually self-correct and make a correct decision, right? And so this extends to arbitrary threshold distributions, not just bimodal distributions. You can have continuous distributions. If you have fast deciders, if you have this group with a low threshold, then the decisions of the entire populations are going to be much better than if everybody has the same threshold. Right, so this is just a general conclusion from here. Right, so okay, so this is essentially what I've said. I'm going to skip this model with correlated information because I'm going to try to keep it in time. And go to this part on early decisions reflect biases, slow decisions do not. So this is what the title of the talk was. So here we're going to take exactly the same model. The difference is that the initial belief, so when you start, the log likelihood ratio at time 0 is not necessarily going to be 0 anymore, right? That was what we had before. You start with essentially with equal distance between the two thresholds. We said the two thresholds were symmetric. In this case, the two thresholds are no longer necessarily symmetric. Could be symmetric, but they're no longer necessarily symmetric. And the amount of how close you are to a particular threshold reflects your bias, right? The more you believe that option plus or option minus are actually true, right? If you're really close to -1, in this case, the threshold is -1. If you're close to the threshold -1, then you start out at time 0 with a belief that the negative option is much, much more likely, as given by log likelihood ratio, than option plus. and the other way around, right? And so what you see here is 1,000 simulations. The first decider, the first person to cross the threshold, right? The first agent or the first of these random walks to cross the threshold essentially just zooms almost directly to the negative threshold, to the one that's actually closest to it. The last one to decide wanders around quite a bit, and the more, of course, the more of these random walks you have, the more this last one is going to run to wander around before hitting a threshold. So the question is, what is the difference between who decides first and how likely are they to be correct, meaning hit the right threshold, and how does that compare to the ones that are late on? How likely are the ones who decide late to be correct? How likely are they to be correct, right? And so the first thing you see is that the probability that the first decision is made by the one with the most extreme initial belief. Meaning the most extreme initial belief is the one that's closest to the threshold, right? That's the most extreme. So the one that's the most biased. That probability goes to 1. So the first decisions are always made by the ones, at least in large populations, and it's the size of the populations, by the ones who hold the most extreme initial beliefs, right? And so this is, again, the asymptotics. These are the asymptotic, the numerical solutions are in X's. The asymptotics that I'll give you on the next slide are in the solid lines. Okay, so you can actually find this probability that the first decision is made by somebody holding an initial belief xi. So this is the initial log likelihood ratio. This is the form that this takes, right? This is essentially log n. This power is the one that matters, and the power is given by a ratio of the distance to the closest threshold to the most extreme initial belief. So Li, the distance to the closest threshold, is Li over L0 is going to be greater than 1, except for the individual, for the agent who holds the most extreme initial belief, and in that case, it's going to be exactly 1, right? And so this is the prefactor, which can also be calculated. It goes over here, but the asymptotic behavior is really governed by this, and this is the 1 minus beta I term, which is going to be negative for any agent whose initial belief is less extreme than that of the most extreme initial belief. And therefore, if this is negative, then this n over log n kind of behavior is going to give you the probability that that's the first decider. That's the person who decides first. That probability is going to go to 0. The only one that doesn't go to 0 is the one where Li, the initial belief, the distance of their initial belief, is actually the most extreme one, right? This is exactly what it's like. The most extreme ones are the ones with high probability make the first decisions. If the diffusivities are unequal, right? So remember, we're looking at the same model here that I've decided before, but the diffusivities could be different between the agents. If the diffusivities are unequal, you can get the same result, but it's not just the distance to the threshold that matters, but it's the diffusivity timescale. It's the distance to the threshold squared divided by 4 times the diffusion constant that actually determines who's going to be close. So the ones that have the smallest diffusivity timescale, this if you think about it, this has the dimensions of time. The ones that have the smallest diffusivity timescales are the ones that are going to make the first decision. They're going to be the ones who reach the threshold first. And again, this can be this agrees with the simulation results. Okay, what about late decisions, right? So this is all the early decisions. The learned decisions are made by the ones who have the most extreme beliefs. If the diffusivities are different, then it's essentially the same thing, but you account for the diffusivity timescales. What about late decisions? So so here what you do is you take the following. You take the probability of that the late decision is equal to theta, right? Is correct, or hits the person who decides last hits threshold theta, is given by the probability of hitting the upper boundary, right? The correct decision in this case. We assume the upper boundary to be correct. That's kind of arbitrary here, right? When starting at a point x, integrated against the quasi-stationary distribution, right? The quasi-stationary distribution is the distribution of beliefs that you would have if you have not made a decision until a really long time, right? And so you condition on the probability that you have not hit either threshold up to some really long time, and you look at the probability distribution of all those beliefs, right? And so this is called the quasi-stationary distribution, right? And so this kind of makes sense, right? So this is a distribution of beliefs that you would have if you have not decided for a very long time, and this is then the probability that if you start at X, you actually hit the right threshold theta, right? And so you integrate these against each other, and that gives you the probability that after a long time, the last person, right, which is going to have to wait for a long time to make a decision, is actually going to make the decision corresponding to the threshold theta. Surprisingly, if you plug these in, you can actually solve this. This integral is kind of nasty, but it's actually not that hard. You can solve this integral, right? So you put these in. All right, sorry. You can solve this integral, and you find this expression. It's a very simple expression. And you find that this is actually the same. So the probability that the last a person makes a correct decision, it's the same as the probability as if they started at zero, if their belief started at zero. So they make a decision as if they were not biased at all initially, right? And so I don't know, there's probably a very simple argument about how to, based on Bayesian statistics on how to get this. I don't know what that argument is. And, I'm sure I'm going to give this talk once and somebody's going to explain it to me and it's going to be obvious. But right now, we only know how to do it via this kind of complicated integration. OK, all right, skip this. So this is the simulation again. So if you flip a coin and then decide on whether to have a positive drift or a negative drift, whether the positive or the negative decision is correct, and you perform a simulation, then the first ones to decide, this is a population of 1 million, the first ones to decide are always going to decide according to their initial bias. And half of the time they're going to be correct, half of the time they're going to be incorrect, right? The last ones to decide are going to make a decision that's essentially the same as if the probability, the accuracy, the probability they're going to make a correct decision is going to be essentially the same as if they started without an initial bias, right? And so early deciders decide according to their initial bias, regardless of the evidence. Late deciders respond as if they had no initial bias. And everyone is equally confident in their decisions, right? Because the threshold determines how confident you are in a decision. That's the log likelihood ratio. That's essentially determines your posterior probability that tells you how confident you are. All right. And so in conclusion, so humans and other animals accumulate social and private evidence to make decisions. This process can lead to rich dynamics, as I tell you. This is a particular assumption that we made in these in this particular study. You can make other assumptions on how information is exchanged and so on, but they were all going to lead to pretty rich dynamics. So I've shown that decision order, I didn't talk about correlations, but there's another part, and information exchange can have counterintuitive, non-obvious effects on ideal decisions. And so kind of where to go, the impact of bounded rationality is unclear. So I've only talked about perfectly rational agents, right? So they use all the information that they're given and make the best decision possible given that information. So what if you discard something, or if you use use information imperfectly? That's unclear. And what we're also doing is extending to multiple choices. Of course, here we have you're deciding between two choices. You can also have multiple objectives. The outcomes do not have to be just positive and negative. You can have multiple outcomes. So these are multi-objective problems and so on. So we're all thinking about those things. So, and that's it. I'll stop here. Thank you. Thanks again for listening. And I will stop sharing, and I can start sharing again if there's questions. I can go back to the slide.
Thank you, Kresimir. Very interesting, very big, I think, topic. I don't know if anyone has questions to share. If I may start with one question. This is new to all of us, so probably I mean, I think my question is pretty basic.
Sure.
Could you go back to maybe the fifth slide where you introduced the problem with two agents and the second agent that only that has information about the decision as well?
This one.
That one, I think. Oh, the next one. I think in the next one you get the model of this one.
Yes.
So
right. Yeah.
So in this case, I wonder, maybe my question is like, couldn't this be weighted? This addition, the private versus social info, could be weighted, because I think I will trust more maybe agent X than agent
absolutely.
Y. And if you have ever kind of considered this influence, yeah.
So absolutely. So what you can do, you certainly, one way to weight it is, so here the idea is, right? So we're looking at optimal agents, right? So Bayesian agents. Mm-hmm. And so if they know each other's threshold, right, then you're going to trust the ones who have a higher threshold more than the ones who have a lower threshold. So it's going to be, there's an automatic weighting, right? And so if I know that you are very careful in your decisions and you take a long time to deliberate and you need a lot of evidence to make a decision, meaning your threshold is high, I'm going to use this is going to be large, right? The theta that I have is going to be large, right? And so often when you have Bayesian, Bayesian theories, if I don't know what your threshold exactly is, then I capture that with some probability distribution. So I do not necessarily have to know exactly what your threshold is, but I have to have some probability distribution over a threshold. And then typically what happens is you integrate over that threshold. Like I find an expectation or, my expected threshold, and then use that, right, to update my belief. So absolutely. It can also, but you can vary this in many different ways, right? So this can be, there's what's called, one model that we looked at was where I believe that everybody else shares my threshold, right? And so that's an assumption, right? That if I'm a fast decider, I decide everybody else is a fast decider. And if I'm a slow decider, I decide everybody else, it's just and that's a common, there's a common, sorry, I forget what the name is, but that's a common assumption in psychology. And you can then vary that in different ways. That's a good question. Yeah, that's one of the main things that really comes into this is this threshold, because that's going to determine what your update is going to be.
So the
weight
is a function. Yeah. Just to understand. So the weight is a function of like the wisdom of the other person, let's say.
Exactly.
Like wisdom is how much evidence I need to believe something.
So hold on. I would call it a little bit. So wisdom, I think wisdom is typically something you have prior to making a decision, right? Prior to integrating information. So wisdom, and we can talk about, there's a semantics, but but I would think wisdom would be more captured by your initial bias, right?
Yeah.
So your initial belief at the outset, before you start accumulating information, if you have wisdom, your bias is going to point you into the right direction, I think.
Yeah. So that's why the weight of the social information, as I understand, it's weighted by the theta of the other person, right?
Exactly. Yes.
So if
the
other person has more wisdom, then their theta will be higher. Then indirectly, I will be weighting by their wisdom.
Right. You'll be weighting again. I would say I would be weighting by by the quantity of, really what it is. It's the quantity of information that that they need, right?
Yeah.
I need, if I know you need, I guess you can call it wisdom. Yes. If I know you're going to need, you're going to need to observe if I watch you and I know you need to observe the coin at least 100 times before you make a decision, right? Or you're going to need 100 tails over heads to make a decision. I know that I can trust your decision much more than that of somebody who's going to toss it a few times and then make a decision, right? So that's kind of where
Yeah.
your
No, it
where the difference comes from. Yeah,
makes sense. And
yeah,
it's a light. I mean, it's a very efficient way to put this hypothesis, because I would have expected, no, we need a matrix of trust or something like that to put it into the equation. But it's not needed. That's a good assumption.
no, yeah, you can make it certainly, right, and that's what I'm saying. If you have bounded rationality, then things become much more difficult. And then exactly
mhm.
in that case, you probably have to have a matrix, and you have to be careful about your assumptions and so on.
Yeah. But well, before any other question? Uh, Anyone else? The question? I will mute myself if you want to speak. I think can.
You want to congratulate the Josic for his talk.
I can't hear very well. Sorry. Can you?
Okay, right now, yeah.
Can you hear
better.
me? Yes, thank you.
No,
Yes, yes.
I just want
better.
to congratulate you for your talk. It was great.
Thank you. Thank you. Appreciate it.
Yeah. Well, I still have one more question, which is
Absolutely,
I think it's the hard question. This
Which is what?
later, maybe. Can we think of the question divides in 2 points, because it's a very interesting setup for doing simulations to work with students to see the impact of decisions, the propagation, like very much more interesting than the icing model that we see in physics, that you get the ferromagnetism. It's a little bit of at the simulation level will be something like that, but it's much more interesting when we think these are people's decisions or animals' decisions. But then what if the decision implies an action that makes an impact in the world that is observed? So
okay, yeah.
have you
Right.
I mean,
So I'm
thought of that?
so I'm working.
Setup?
So I hope that next time we meet I can tell you more about it, because I'm working with Chris Bauch, who is on to model essentially people's opinions about climate change and decisions about climate change using this particular framework. Mm-hmm. So Chris is a much better. Chris knows much more about. So Chris comes from epidemiology, so he is, but he's also started working on opinion exchange, and in particular, he looked at dynamics of vaccine hesitancy. So he looked at how people's opinions about vaccines are influenced by epidemics, right? So he has a pretty good background in trying to looking at models of how decisions impact behavior, and how behaviors impact decisions, right? How other people's behaviors impact decisions of individuals, right? Mm. And so behavior in this particular case, in the vaccine case, is a decision. In climate change, it's an expressed opinion, and so we had to change the model a little bit to look at sequences. Mm. So I think we have something interesting there. So hopefully it's going to come out in a couple, in a few months as a preprint. And the other thing we're trying to do, which is different, is we have a grant, and I don't know if it's going to be funded. It should be interesting. Is to have people. So this is completely theoretical. That grant would fund people in virtual reality interacting, right? And so the idea is that they gather information in a controlled way. And the reason to do it in virtual reality is because you can control what information they gather, right? So what observations they make, and you can exactly control what information they exchange, right? And so the idea is that we don't allow them to talk, which is limiting, but to only communicate their decisions, right? So they can, you can either 2 or 3, they can make a few recommendations. There's not just 2 H plus, like here, H plus H minus, sometimes more, but they only can communicate their decision and their confidence, right? And so you can control exactly what evidence is accumulated and what evidence is shared, right? And so hopefully that will allow us to see a little bit more about how well these models describe actual human behavior.
this is super interesting, and it gave me an idea to think. Maybe we can discuss it later, but I don't know if you're familiar with these blockchain ecosystems.
No, what is that? Tell me more.
So, blockchain, like Bitcoin kind of thing, like you can have money in the tokens in a crypto, like Bitcoin, like setting in a blockchain. And there is a lot of research on decentralized governance. So trying to create structures where people can make decisions. You control the information they get, you control, like, ideally it's supposed to be super open. You can see what others vote, and you can see how many tokens they invest on their vote. So if you want to make a company decision, an ecosystem decision, are we gonna merge with, I don't know, with Ethereum? Are we gonna allow for this new project to come in and so on? It's all like decentralized governance, decision making. And as far as I know, you can bet on the likelihood of this to be right, by investing your own tokens. So then people will be paid back with assets from the new business, because they invested more on it at the very beginning. They believe, they accepted. So there's a lot of research, or lots of models, I would say, more than research, people proposing models in the world of blockchain ecosystems. And I don't know if you want to know more about it. I'm kind of slightly connected to some of this, and they have grants to support this type of research themselves. They want to know more about how they function. So this framework.
Is there, if you have a review, you can send it. It's like something, I'm sure if there's tons of paper, it's hard to get into. But if there's a review paper, I'd like to see it. If you know of one,
I'll check.
But why the blockchain? I mean, why do you need the blockchain? Why not have essentially like a voting market, like Polymarket or Metaculus, or Predicted, or one of those. Why not just have where you just make a prediction and then have it resolve after given amount of time? Why do you have to have a blockchain?
I don't restrict to only to blockchain, but I think that the motivation of having a decentralized governance system, it's pretty strong on them.
I see.
So they want to know more what could be the ideal sizes, the ideal time to wait. So you have a theoretical kind of bound to say this is the right decision at the collective level without any kind of centralized, that's more like.
I see. Without Got it. Yeah. No, that makes sense. Yeah.
I will share that with you. I will check it out. And
please. That sounds interesting.
This is it. Thank you very much, Kresimir, and for your amazing talk. It will be published in our YouTube channel later on, distributed on our kind of Instagram, our channels. So thanks a lot for coming.
Right.
And I hope.
Thanks for having me.
Soon. Yeah. Bye.
Bye.
Bye.